Example 6.4.2. Okay, this one says, suppose a 10-year, $1,000, 3% Treasury note with semi-annual coupon payments is priced at $1,090.23. What is the yield to maturity at the current price? Okay, and if you watched the previous example, 6.4.1, you're probably already screaming the answer at it. But again, I wanted to use the same cash flows here, so we're not getting confused and getting lost in different kinds of numbers, but we can instead focus our attention on the relationships here. How are price and yield related specifically is what we're going for on this one. So we've got a time value money problem. We're going to use our three-step process. I'm mapping out the cash flows. And the trickiest part with bonds is getting from the bond description, especially when we've got coupon bonds, getting from the bond description to the actual cash flows. Because we've got some calculation we need to do instead of just mapping it straight out. We've got to get from the sort of cryptic bond description to what the actual cash flows are. All right, we talked about in the previous example that the 10-year is just the time to maturity. That's when the last payment is made 10 years from today. $1,000 is still the face value of the bond. The 3% that's with the face value is the coupon rate. So this percentage, although we've been using percentages as discount rates, we will not use this guy as a discount rate to evaluate any cash flows. The only thing we'll use the coupon rate for is to find the amount of the periodic coupon payment. Right? It's just the percentage of face value. The coupon payment, or coupon rate, is the percentage of face value that the bond pays out in interest each year. All right, so we've got the coupon rate. We talked about it being a Treasury note because it has 10 years to maturity. It's a U.S. government bond, and they just have different names depending on the maturities of the bonds. And semi-annual coupon payments means that it is making a coupon payment, which is an interest payment on loan, every 6 months or twice per year. The current price is, of course, the price. That one's thankfully not cryptic. We kind of know what a price is. And then what we were looking for is the yield to maturity at the current price. All right, so let's map out what we can, and we'll talk a little bit more about yield to maturity. Before we can map the cash flows out, we've got to figure out what they actually are. So we've got to use this coupon rate to actually get to the coupon payment. And we're going to do that using this equation from Chapter 6. CPN stands for coupon, and that is the actual amount of coupon payment. That's equal to the coupon rate times face value, right? So that'll give us the total amount of interest that it pays out each year. And then we're going to divide that by the number of payments per year to figure out the amount of each actual payment. So the coupon payment is equal to the coupon rate times the bond's face value. And then we're going to divide that we're going to divide that, and if all that effort to make a straight line was worth it. Oh gosh. We're going to divide that by the number of coupon payments per year. All right, so for this bond, our coupon rate is 3%. We're going to do arithmetic with it, so we need to express it as a decimal. 3% as a decimal is 0.03 times $1,000 face value. And we're going to divide that by the number of payments per year. This one's semi-annual, so it's making payments twice per year. All right, 0.03 times 1,000 is 30. So it's paying $30 per year in coupon payments, but it's making payments twice per year, so it's going to pay half out every 6 months. So every 6 months, this bond will pay $15. Okay, once we've got that, we can actually map this guy out. All right, we know the price, so we can go ahead and put that in. It's the $1,090.23. I'm going to look at this from the investor's perspective, so I'm going to call that a cash outflow of $1,090.23. So if the investor were to buy this bond for $1,090.23 today, he or she would then receive a cash inflow of $15 6 months from today, another cash inflow of $15 6 months after that. And so these two tick marks here represent a 12-month period or 1 year. So we're actually keeping track of 6-month periods with this timeline because that is the frequency of the cash flows. All right, so every 6 months, our bondholder would receive a cash inflow of $15, and that pattern would go on. I'm just going to do our little broken squiggly marks so we don't have to draw out so many of these things. That's going to go on for 26-month periods, and it's 26-month periods because it's a 10-year note, and it's making payments twice per year, so there'll be 20 total payments. Okay. And at the end of year 10, or the 26-month period, our investor will get the last coupon payment, and will also receive the face value. So the question that we have to answer is, what is the yield to maturity? Where the yield to maturity is defined as the discount rate that equates the present value of all the promised future cash flows, so all these coupon payments of $15 and the $1,000 face value payment. If we discount all of these back to today's dollars, then the rate that makes the present value equal to $1,090.23 will be our yield to maturity. All right. We also talked in the previous example about what type of cash flow we're dealing with coupon bonds, and we can think of it as a combination of two types of cash flows. If we look at just the coupon payments, we've got an ordinary annuity, because we've got level payments at regular intervals happening at the end of each period, and they're finite, they stop. So that's our ordinary annuity. And then the face value is like a lump sum cash flow, if we look at that by itself. So we know that's what we're dealing with. Step 2 is to identify the type of cash flow we're dealing with. And we've got a combination of an ordinary annuity. That's the coupon payments. And then also a lump sum. That's the face value. Right? And I know we went through all this in the previous example as well. I don't know what your entry point is going to be in these videos, so I'm going through it again. So if you already know how to map this out, what type of cash flows we're dealing with, feel free to skip to where we're actually solving the problem. Step 3 is to select our tool to solve for this thing. Well, we can use the present value of an ordinary annuity and a lump sum formulas to find the price, right, or equate the price to it and solve the rate. We can also use the time value money keys for these types of cash flows, and we can also use the spreadsheet. I do, in this case, want to look at the formula just so we can see what's going on, and you'll see why we are not actually going to use it. But I think seeing the setup helps build some intuition for what's going on here. So for the price of a bond, we call it PV of a coupon bond on the formula sheet. We have a combination of the present value of an ordinary annuity, so the payment, first payment, divided by the interest rate times the quantity, 1 minus 1 plus the interest rate raised to the n. This is the present value of an ordinary annuity formula. This will give us the present value of the coupon payments, and then we're going to add to that the present value of a lump sum formula, and this will give us the present value of the face value. Okay, now let's plug in what we know here and see what we would have to do to solve for this. We actually know the price of the bond. That's the $1,090.23. We also know the payment. That's 15 divided by R times. We know N, that's 20. And we know the face value. Okay, so what we would have to do if we were going to use the formula to solve for this bond, is we would have to find the little r that makes this statement true. Ordinarily, we could do some algebra and get r by itself on the left-hand side and figure out what it is. Well, in this case, we're not going to be able to do that. We've got r in the denominator here raised to the 1. Of course, we don't tend to write that. And r over here is added to 1 and then raised to the 20, and then the same here. There is no way to use algebra to get r by itself. The only thing we can do with this type of problem is look at it and take a guess. And we also talked about in the previous problem, we know this thing is trading for a premium, so we know the yield must be less than the coupon rate. The coupon rate's 3%, so we'd probably start at something like 2% and see what happens, right? We plug in, actually 0.01, we'll talk about why in a second, but we would plug in the equivalent, a yield of 2%, and see if it made this equation true, and if it didn't, we would just adjust our guess and do it again. Well, the time value money keys on your calculator or on a spreadsheet does the exact same thing. It can just do it a lot faster. It can guess over and over again a lot quicker than we can. All right, so n is 20, I over y is what we're looking for. In this case, we know the present value. I'm looking at it from the perspective of the investor, so I'm going to record that as a cash outflow of $1,090.23. That means the payment, the coupon payment, will be a cash inflow of $15. And then the face value will also be a cash inflow of $1,000. And we're just going to find the rate that makes that true. All right, so let's plug these guys in. We'll start by clearing it out. Second, clear TVM to zero everything out. N is 20, and really if you had worked the previous example and these numbers are already in there, you can just reuse them. I'm going to pretend like I hadn't just worked this problem. Okay, present values minus a negative 1,090.23. Payment is a positive 15, and future value is a positive 1,000, and I'm going to say compute I over y. Okay, I'm getting 1 here, and here's where we have to be careful with the definition of yield to maturity, because the problem did ask for the yield. What is the yield to maturity at the current price? Well, yield to maturity has a specific definition. It is, we've talked about the definitions, but one part of it is that it's always expressed as an APR, or annual percentage rate, with the appropriate compounding. And the rate that we just solved for is not an annual rate because the cash flows are not happening annually. This N of 20, that is 26-month periods. So what the calculator just gave back to us is the 6-month effective rate. All right, this is what we have been calling a little r up through chapter 5, up through this chapter as well. Okay, it's the periodic effective rate. So since yield to maturity is always expressed as an APR, we're going to use the definition of APR to convert this thing to an APR. Right, where our little r that we just solved for, the 6-month effective rate, is 1%, and we're going to multiply that by m, which is the number of compounding periods per year. In that case, that's 2. So our actual APR is 2% for this one. And so our yield to maturity would be quoted as 2% for this bond.